Let us begin. Good evening, everyone. I'm Anish Shambekar, PMRF and PhD candidate from Aerospace Engineering ISC Bengaluru. Welcome to this week's live interaction session for the NPTEL course Dynamic Behavior of Materials. The course code is NOC24ME102, and this interaction session is dedicated to the week 7 content for this particular course. The outline of what was discussed in this course is as follows. We first had a brief about complex problems in shockwaves, particularly about temperature rise. We also then looked at shockwave attenuation and finally moved ahead with shockwave interaction. So, temperature rise in shockwaves. We have seen that shockwaves typically have a very sharp pressure front, shock front, which is very thin, that passes through the material. When it passes through a material, it compresses the material very rapidly. So, like because the shock front is thin, and the pressure differential is very high, you can think about material being compressed very rapidly into a very small volume. So this is the outline of what was discussed in this week's lectures. So the first part was about temperature rise associated with shock waves. You have a very thin shock front. So in terms of length as well as using shock wave velocity in terms of time, you have the shock front passing very rapidly through a material, and there is a large pressure differential associated with it. We have already seen that this happens under certain conditions of high pressure and hydrodynamic uh, loading and assuming no shear loads and so on. So it happens very rapidly. The material will be subjected to a very large pressure differential in a very small time, which means that the material gets compressed very quickly in a very small amount of time. So in shock waves, you have compression of material, and this happens very quickly, leads to decrease in volume, right? This overall, this leads to an increase in temperature. This because the front is very thin, shock front is very thin, or the plateau rise that we have seen is usually short. What we can do is we can assume this to be an adiabatic process, which means that there is no heat exchange with its associated neighboring particles or neighboring material. Whereas when we have release, it goes from shock state to initial state. It has been observed that this usually follows an isentropic process. So in case of solid materials, we were to draw a pressure volume diagram. So specific volume, this left hand side is the pressure, y axis is the pressure, and if this is my V naught, this is my initial pressure P naught, or could be also the ambient pressure. You would have your shock U unit. It would take it to say, some volume, compress it to a volume V1, increase the pressure to a point P1, and shock U unit. And then you would have release isentrope. So this is the release isentrope. So we can see that in this process there will be some amount of energy that goes that that is lost in the system. So that would be given by the area of this PV diagram between the two processes going to shock state and coming back to the initial state. We'll also see that your T2 then T naught. Okay. So the there is some amount of mathematical jugglery involved wherein we could start off from Mie-Grun's equation of state as well as use the set of thermodynamic relations to find some relation between say temperature T1 at this point and T2 which is the final point. So that part is out of scope for this syllabus, so I'll not go into that. The next part was related to shock wave attenuation. So if we draw a typical shock wave, so pressure versus distance plot at different distances, you usually have your short flat top ahead of which you have your shock front. The shock front would move with some velocity us. There is usually an associated elastic precursor C naught elastic wavefront, and then there is a release associated. This profile is generated usually during plate impact, whereas you could have another profile which is of interest is this one. Would have a near triangular profile, shock front, release part. This is usually generated by lasers. Or I think also using detonation explosives. So what we see is with increase in pressure, your shockwave velocity will also increase. So you could have a scenario where, like at very high pressure, US exceeds C naught. But for most of the cases that we'll be looking here, US will be less than C naught, which means your elastic wavefront will propagate ahead of your shock front. Then, if I consider a case of a projectile hitting a target, we'll see what happens. So this is going with velocity v. I'll assume t equal to 0. This is increasing t 0. We'll assume same material in both projectile P and target T. Okay, when at the point of impact T equal to T1, you would have projectile P target T. You would have some disturbance which starts to propagate from the projectile target interface into both the target as well as projectile. This would normally involve both elastic wave and shock waves. Elastic and shock waves can be generated. Again, it's dependent on the velocity v, but usually, since we are looking into shock waves, we'll assume that velocity v is sufficiently high to generate both elastic and shock waves. What would happen now is, after a while, this pressure that is generated of the interface, it will finally reach this free surface. Here, I will say, suppose this is the shock wave, elastic wave rate EW, shock wave rate SW. This is the behind the shock wave. Suppose this is C naught, RW. RW will be release wave generated after interaction with the free surface. So the release wave will basically make the stresses to zero. So the release wave as will be an elastic wave with with the velocity v naught, again same material. So that c naught release wave will slowly start catching up to the shock wave. Notice at this point that your release wave is at free surface with c naught, whereas there is another elastic wave moving into the target with c naught. So there will be always some amount of material which will be elastically deformed, and assuming that the target is like infinitely or like very long in the right hand side direction, you'll have a that small amount of material which will be constant, which will be always be deformed, and that deformation will move ahead with the elastic wave velocity c naught. This release wave will overtake, will start slowly catching up to your this release wave will slowly start catching up to your shock wave, and then you'll have a scenario where I'll just draw the I'll just draw the target. I'll just draw the target now. This is the target. You have your release wave coming up. Release wave. This is your shock front. This is moving with US. Somewhere here your original elastic front C naught has propagated. When the release wave moves forward, it will have particle velocity UP release wave as C naught plus UP, and shock wave will have velocity US. So you will normally have C naught greater than US, so which means that your release wave catches up to catches the shock wave. So eventually you would have a point that looks like your release wave will basically overcome your release wave will basically overcome your shock wave. Three stick. Okay. So how does this look like graphically? You can think of it as follows: E equal to T1, you have this is X, C naught, US. At T equal to T2, you'll have your release wave, or I should write T equal to T3, where release wave starts to catch up. You'll have a profile that looks like this. Your flat top has become shorter, and then eventually, say at T is equal to T4, your release wave finally catches up to your. Okay, so this is actually pressure versus distance. So these are wave profiles across pressure versus distance wave, pressure versus location wave profiles across, like snapshots across different moments of time. There's one more thing. So normally we say we would have, if we have a humanoid, normally we would have this is 1 minus 1. Normally you would have a pressure versus specific volume, and can you connect curve. This is for the case of ideal hydrodynamic model, where all your where your pressure state is simply sigma xx equal to sigma yy sigma zz equal to minus p. Okay, suppose the shock wave is moving along x-axis, then we can, in the real case, you would have, suppose a volume which looks like this, and after passage of shock wave, it will say be compressed to a point like this. So L naught, L naught, L naught, and this portion is L. So your epsilon x is L naught minus L upon L. Your epsilon y is equal to epsilon z equals 0 after passage of shock wave. So shock wave moving along x-axis compresses the material along x-axis, whereas there is no strains developed around y-axis. When that y and z axis, when that happens, this is basically uniaxial strain. Then you can write epsilon x is equal to 1 minus, I can L by L naught into L naught square by L naught square, which is nothing but 1 minus V by V naught. Right. When you have non-hydrodynamic case, non-hydrodynamic stress, with HEL, which is the humanoid elastic limit not negligible, then you have a case where elastic deformation occurs first, and only then you have only then plastic deformation. Here the condition for plastic deformation is stress is sigma yd. This is the dynamic yield stress. Going back to our solid mechanics, we can write pressure as 1/3 of trace of the stress tensor sigma xx plus sigma yy plus sigma zz. In the case of uniaxial, in the case of uniaxial strain, you have same stresses along y and z. So you can write third of 3 sigma x plus minus twice of sigma x minus sigma y. This sigma x minus 2/3 of sigma x minus sigma y. This we know from like Moore's circle, it can be represented as 2 by 3 into twice of tau max. For plastic deformation, we know that tau max equals tau yd. At this point, the plastic deformation will start. Therefore, pressure can be written as sigma x minus 4 by 3 tau yd, which means sigma x is pressure plus 4 by thirds tau yd. So if I again plot my curve, sigma x is equal to 1 minus v upon v naught. My Rankine-Huguenot ideal case would look like this. It has no elastic deformation preceding plastic deformation, whereas my real material, which has some elastic deformation till Huguenot elastic limit, and after that it will start following a parallel curve. Similarly, when we unload it, it will again go down. So this is loading, this is unloading. The only thing is like the signs will change around. So you have a net width of one third tau yd. Notice here that the path that the material will take is not reversible. It takes a different path to loading and another path to unloading. So there is some irreversibility due to elastic plastic effect. So it's popularly considered as the hysteresis. Uh, so this is what happens when you have a Huguenot elastic limit and difference in hydrodynamic and non-hydrodynamic components. If we plot how a shock wave looks like at different snapshots of time. Suppose this is how initially looks at t equal to t1, then it will travel. This is x equal to 0, t equal to 0. Then it will travel some distance, after which the release wave will start catching up. Again, this will still travel at, this is up, this will still travel at us2 is equal to us1. After a while, this is 3, this is us3 less than us2. There is a decrease in pressure associated. As the release wave starts catching up, you for lower pressures you will have like the elastic component of the wave going on. So at higher pressures you have your shock wave component, and the release wave will move ahead with elastic wave velocity c naught. So it will eventually catch up with the shock wave components at higher pressure, and then you will have the total peak pressure which comes in the shock wave profile. It will start decreasing as the release wave starts catching up from the top. Then another snapshot would look something like this. Here you'll have US4 further lesser than US3, right? So there is a decay of pressure pulse as it travels through the material. Release wave will move with some velocity c naught plus up, which will be greater than us, which is shock wave velocity. At snapshot 3 or case 3, you have the case where release wave has overtaken shock wave. This leads to reduction in peak pressure. At this point, your pulse duration or pulse stop duration becomes zero. Okay, so after pulse duration Tp goes to zero, your peak pressure continuously reduces, keeps on reducing, which means that your shock wave velocity also, US also keeps on decreasing. By using advanced computational methods, we are able to estimate fairly how the shape of pulse changes as it moves ahead with time due to interaction with the release wave. We define attenuation rate of rate at which the pressure pulse dissipates itself as it moves through the material. So there are uh, a lot of reasons associated with this, but most of it boils down to, or rather, the primary thing it boils down to is how the material microstructure looks like. So whether you have voids, whether you have any other kinds of defects which interact with the pressure pulse as it moves ahead. So that automatically causes some loss of energy. Secondly, as we have already seen, the thermodynamic process involved for a material to go from an uh, free state to a shock state and then back again to a different pressure free state is it's irreversible. There is some amount of energy loss associated with it. So, like this attenuation would happen either way. If we wish to try and understand how quickly we'll write this down, previous one. Energy dissipation usually due to heat in form of heat, energy can dissipate. There may be some defects in the material. There could also be other processes involved. So usually, the way the release wave will come along is it will be in a more concave manner. But if we assume that the release wave is just coming along like flat, like a straight line, so it would normally be concave like this. But if we assume that it's simply coming along a straight line, then we can get a very rough estimate of the amount of time it requires for the rather the distance the shock wave would travel in the material before its peak pressure starts dropping. So a very simplified model we can use, wherein what we say is that suppose the distance traveled by the shock wave is S in the material. This is my target T. This is my shock wave. It is moving with S US. This is the distance X S, and this is my release. So release wave also will start matching it. So we got shock wave and release wave. So the distance traveled by the shock wave S is US into T. In the same time, you have uh, your UP plus C naught S plus X is UP plus C naught into T. Here what here X refers to the initial thickness of the pulse. I should write XP, initial thickness of pulse, from which you can write US by S is equal to UP plus C naught upon S plus XP, which gives S into UP plus C naught is equal to S plus XP into US, which is nothing but US into S plus TP being the pulse width in time into S into US. So if we simplify this, you get an equation which looks like S into UP plus C minus US is equal to US square into TP, which gives S is equal to US square into TP upon UP plus C naught minus US. So this is a very first order estimate for the amount of distance shockwave would travel without losing on its peak pressure. This ignores a lot of things, especially how energy is dissipated in any other manner, because there is not only the release wave, as we have discussed. There is not only the release wave which will cause drop in pressure. There is also other factors are also involved, particularly those relating to material microstructure, as well as the irreversibility of process of this material microstructure, irreversibility of the shockwave loading and unloading process. So there were a few experiments done. So I'll just quickly go through their key result. This one was done by I think Earthman in 1966 with aluminum target plus aluminum projectile. We are plotting velocity versus a relative ratio of target by TP. Here we are interested in predicting attenuation using uh, between we are interested in comparing attenuation between experiment and some chosen model. So this could be the simplest model could be hydrodynamic theory. So the hydrodynamic theory gives a velocity plot like this, whereas the real experiment looks something like this. So Another one. This is an advanced Q code model. Another set of experiments was done by Zhu et al. This was done in 1981. You have a plate impacting on nickel, and they basically studied effects of metallurgical aspects such as say grain size. They concluded that there is no significant effect on attenuation. So if this is a plot of pressure versus distance at different locations. Suppose the initial pulse looks like this. After a while, release wave will catch up. After another while, you'll have drop in the peak pressure. So the experimental plots that they had were this is close to the interface, close to impact interface. This one is about 10 centimeter from impact interface. This these dots are basically your hydrodynamic projection prediction, which means that your hydrodynamic prediction predicts much less attenuation. It's also observed to work well near impact interface. So as we go farther and farther away from the interface, our predictions go more and more haywire. Okay. The final part for this week's interaction lessons was related to how shockwave interacts with a boundary. So suppose you have two mediums with two different shock impedances coming together, two different material properties. You have say V1, US1, Rho1, V2, US2, Rho2. How a shockwave would move in. You know that Rho naught US is your shock impedance. It relates your pressure with particle velocity. The easiest way to do this is using impedance matching technique. So this allows us to transfer of shock wave between media. So the first case is low impedance A to high impedance. I draw the pressure versus particle velocity plots. So we have seen these plots in fifth or sixth week lectures wherein we plotted how pressure and particle velocity relate to each other. So suppose this is plot of medium A has a pressure P1. Then in case you have impact between projectile and target of same materials, we have seen that at the point of contact you have velocity which equals to half as much of particle velocity which is equal to half as much of the impacting projectile velocity. So by that reasoning, we sorry, draws reflected curve around this point. This is UP1. This is A reflected. And what we do is we see how the impedance curve of B intersects. So it will intersect at a point like this. So this is UP2. So if I plot the pressure profile, it would look like this is the interface. Material A, material B equals 0, equals T1, equals T2, T3. Well, pressure pulse P1 approaching the interface. Then it hits the interface, creating a creating an increase in pressure at the interface because B has higher impedance. It's also seen from the pressure and particle velocity plot. This is P2, it's P1. Then P1 and P2 will interact again, and you will end up having a after a relatively larger amount of time, you'll have end up having a reflection with pressure differential P2 minus P1. The pressure pulse P2 moving along. Okay. The pressure pulse now will move ahead with a lower velocity UP2 but a higher overall pressure, higher peak pressure. Second case, high impedance A, low impedance B. And if I plot the pressure versus particle velocity diagram, suppose this is the UP1, this is P1. The reflected curve would look something like this, and B has a lower impedance, so look like this. UP2, P2. Again, if we draw the pressure profile, this is A, this is B, this is T equal to 0. Pressure pulse approaching the interface, pressure P1. Once it touches the interface, it will have a lower pressure P2 associated with it. So this means that P is equal to P1. Another time you have small P2, a larger P1 minus P2 being reflected in the opposite direction. This is still P1 coming up, so small amount of some amount of reflection coming back before the end of pressure pulse in medium A itself. T equal to T2. Once this reflection comes along, you will have a interesting case where you have negative pressure, so which is basically your tension associated with P2 minus P1 is equal to T3. So you have a tensile wave formed which can lead to spalling. So if the pressure differential is sufficiently high, you can it can lead to spalling. So one of the cases you can think of it as, if B is basically, if B instead of B you have like free surface, like no material forward, and the reflected pulse would basically have the same pressure going back, and but now in the tensile direction. So you can think of a large pressure of the order of gigapascal going back into the material, and if there are any small voids inside the material, microvoids or cracks present inside the material, then the material will be quickly stretched across the tensile wave, and then that crack may lead to like the crack may expand. There may be a crack growth associated, eventually leading to material fracture. If you have if you have a case where you have two shock waves coming together, two shock waves meeting, think of it as T is equal to T naught pressure pulse P1, both having say same pressure P1. At T equal to T1, the pressure will be combined to some other value P2, will not necessarily be 2P1. So this P2, then you will have at T is equal to T3, you will have a case where only have P2, it's moving in both directions, two fronts, then you have again going back to P1. So in this case, we have shock wave fronts with same peak pressure, parallel to each other. Both have same velocity, both have same particle velocity UP, and then you also see some release waves in between the interaction, and then goes out. So peak pressure rises to V2 corresponding to the velocity 2 UP. So now the pressure. Suppose this is UP1, P1, then you would have something like 2UP1 and P2. So the exact value of pressure is determined by uh, looking at this sort of plot. Do you have any particular doubts related to this? If not, then I think we'll stop for the day. I will see you again in the next one.